Welcome back to the deep dive.
Glad to be here.
Today we're tackling federated learning, FL, right?
That's right, FL.
It seems like a really clever twist on training machine learning models.
It is, especially when you're dealing with, huge amounts of data that's spread out everywhere across devices, organizations.
Right. And the core idea, as I understand it, is you train together on this decentralized data.
Exactly. Collaboratively.
Hmm.
But crucially, without ever having to bring the sensitive, raw information to one central place.
Okay, that's the key. No central data hoarding.
Precisely. And it's really driven by a few big trends, wouldn't you say?
Yeah, definitely. I mean, just the sheer amount of data coming off our phones, wearables, all the IoT stuff.
It's exploding.
Yeah.
And at the same time, people are, quite rightly, getting much more concerned about privacy.
Plus, you have regulations like GDPR, HIPAA. They're drawing some pretty firm lines.
They are. And honestly, just the logistics, the cost of trying to move all that data centrally,
Yeah.
it can be a nightmare. Bandwidth, storage,
Yeah, a huge bottleneck. So federated learning kind of steps in as a solution.
as a really powerful alternative, yeah.
All right, so our mission for this deep dive then is to really get into the nuts and bolts, the technical side of federated learning.
Yep. How it works, the mechanics,
What challenges pop up, where it's actually being used.
and importantly, how it maintains privacy and security. The techniques involved.
Exactly, because we're talking about everything from, apps on your phone, learning your habits.
To hospitals collaborating on disease models, or banks working together on fraud detection, all without sharing the core data.
It's a really wide range of clients.
It is. Mobile devices, edge nodes, entire organizations. Hospitals, banks, universities, each with their own constraints and data.
Okay, so let's start right at the foundation, the core architecture.
Yeah.
How does this decentralized training actually happen?
Well, the most common setup, the one you usually start with, is centralized federated learning.
Centralized. Okay, sounds a bit counterintuitive, but go on.
Right. It uses a client-server model. So there is a central server, but its role is different. It coordinates.
So?
It starts by sending out the current version of the global model to a selection of clients.
Clients like my phone, or maybe a sensor in a factory.
Exactly, those kinds of things.
Yeah.
These clients then take that model and train it, but only using their own local private data.
So the data my phone has about, say, my app usage, that stays on my phone, but is used to tweak the model it just got.
Precisely. That's the crucial part. After this local training happens, the clients send back only the updates they made,
Not the data itself.
never the raw data. They send back things like the changes to the model's weights or the gradients they calculated.
Okay, so just the learning, not the information it learned from.
You got it. The raw, sensitive data stays put on the device within the organization's firewall. It doesn't leave.
Okay, server gets these updates, potentially from lots of different clients, right? What's next? How does it make a better global model?
So the server's job is then to aggregate these updates. And the most common way to do this is federated averaging, usually called FedAv.
FedAv, okay.
Yeah, it's pretty much the standard baseline algorithm. Essentially, the server just calculates a weighted average of all the updates it received.
Weighted. How does that work?
Well, the weight given to each client's update is typically based on how much local data that client used for its training.
So clients who trained on more data have a bigger say in the final average.
Exactly right. They have a greater influence on the resulting global model. This new, improved global model is then sent back out to probably a different set of clients for the next round.
And this just keeps going, round after round.
Yeah, it's an iterative cycle. You repeat it until the global model performs well enough for whatever the task is. It sounds simple, but it's actually quite effective, even with all the complexities we'll get into.
Got it. That makes sense for a centralized, coordinated approach. But you mentioned earlier there are also decentralized versions.
Yes, absolutely. Sometimes having that central server can be a bottleneck, or maybe a single point of failure, or even just a trust issue.
Right. You might not want one entity controlling the whole process.
Exactly. So we also have decentralized or peer-to-peer FL architectures. In these, the clients talk directly to each other. No central coordinator.
No central server at all. How do they coordinate then? That sounds complicated.
It can be. There are a few ways. Gossip protocols are one method. Clients just share their updates with their neighbors in the network.
Like whispering updates around.
Sort of, yeah.
Yeah.
Or you might have ring topologies, where clients are arranged in a circle and pass updates along sequentially.
Okay.
And interestingly, you can even bring in technologies like blockchain.
Blockchain. for coordinating machine learning. Wow.
Yeah, it's a pretty cool intersection. The blockchain can act as a secure, kind of tamper-proof log of all the model updates.
And help them agree on how to combine the updates, like a consensus mechanism.
Precisely. So instead of a server doing the aggregation, the clients themselves reach a consensus, maybe driven by the blockchain rules. It makes it harder for one bad actor to mess things up.
Interesting, but I imagine that adds overhead.
Definitely. These decentralized approaches, while removing the central server, often bring their own challenges. You usually see increased communication delays, more latency, and just more complexity in managing the whole thing.
Trade-offs, as always. Okay, going back to the centralized model for a second. You said the server selects some clients each round. Why not just use all available clients?
Yeah, client selection is really important. It's mainly because the clients in an FL system are usually very diverse, heterogeneous.
Meaning,
Well, not all devices are online all the time. Think of
yeah.
the phone's connection drops, battery dies, and their capabilities vary hugely. Some are powerful, some are pretty basic, different processing power, memory, network speed.
Right, so trying to get everyone involved in every single round just wouldn't work.
It's just not practical.
Yeah.
Or efficient. You'd be waiting forever for the slowest ones, the stragglers.
So client selection is about practicality, but also maybe picking the best clients for that round.
Exactly. The strategies try to pick a subset of clients that are actually available and likely to contribute meaningfully. There are different ways to do it.
Like what?
Well, the simplest is just random selection. Pick a random bunch.
Okay.
Or you could use important sampling. Try to guess which client's updates will have the biggest impact, maybe based on past contributions or their data profile.
More targeted.
Yeah. And there's even research using reinforcement learning to dynamically learn the best selection policy over time, balancing exploring new clients versus exploiting known good ones.
Clever. Okay, so clients train, they send updates. Communication. That sounds like it could be a massive bottleneck, especially with potentially millions of devices.
Oh, it absolutely is. Communication efficiency is one of the biggest hurdles in FL.
So what are the strategies? How do you minimize that traffic?
Several techniques get used. A big one is model compression.
Shrinking the updates.
Exactly. You can use quantization, which reduces the number of bits needed to represent the model weights. Less precision, smaller size.
Does that hurt accuracy much?
There's a trade-off, but often you can reduce size significantly with minimal impact. Then there's sparsification finding and removing less important connections in the model.
Trimming the fat.
Kind of, yeah. And even pruning, which removes whole chunks of the model that aren't contributing much. All aimed at making the update messages smaller.
So smaller messages. What else? Fewer messages.
Well, that relates to another strategy, asynchronous communication.
Asynchronous, meaning not all at the same time.
Right. In the basic synchronous setup, the server has to wait for all selected clients to send their updates before it averages them.
Which could take ages if there are slow ones. Stragglers, you called them.
Exactly. Stragglers can really slow down the whole process. Asynchronous methods let clients send their updates whenever they're ready. The server doesn't wait for everyone.
That sounds much more efficient. Less idle time.
It reduces idle time and mitigates the straggler problem. And one more key thing here is secure aggregation.
Secure aggregation.
Yeah, often using cryptography.
Mm.
The idea is the server can combine all the updates to get the average, but it cannot see any individual client's update.
Ah, so even the server can't peek at my specific model changes.
That's correct. It only sees the combined result, protecting individual contributions further.
Very important. Now, you also mentioned system heterogeneity, these diverse devices, different processing power, memory, battery, network. How does FL cope with that?
It needs adaptive mechanisms built in. The system has to be flexible.
Like how?
For example, some clients might only be able to do partial training, maybe just a few steps, or train on only a small part of their data if they're low on battery or time.
So they contribute what they can.
Right. Or early stopping a client might stop training if it hits a certain performance level or if it's running out of resources. And again, resource-aware client selection comes in. The server might prioritize clients that it knows have enough juice or bandwidth to complete the task effectively in that round.
So it's a constant juggling act, trying to get good updates while respecting everyone's limitations.
It really is. Balancing learning progress with the realities of a diverse and dynamic device pool.
Okay, I think I've got a decent handle on the basic architecture now. Let's dive into those key technical challenges you mentioned. You highlighted statistical heterogeneity, this non-IID data thing. Why is that such a big deal?
Non-IID data.
Yeah.
Yeah, it's probably the core statistical challenge in federated learning.
Non-independent and identically distributed.
Exactly. In traditional centralized machine learning, we usually assume all the training data comes from the same underlying distribution, like it's all shuffled together.
But in FL, that's not true at all, right?
Not even close. Each client's local data can be wildly different. Think about it. My phone usage patterns are shaped by my habits, location, demographics. Yours are shaped by yours. They're not drawn from the same pot.
My news reading habits versus someone else's gaming habits. Totally different data distribution.
Totally different. And this breaks a fundamental assumption behind many standard ML algorithms and optimization techniques.
Okay, so what's the impact?
Mm.
If the data is so different across clients?
It can really mess things up. It
Yeah.
can drastically slow down how quickly the global model converges, or if it converges at all.
And the final model might not even be very good.
Right. You can end up with a global model that actually performs poorly on the local data of many clients. It might be okay on average, but bad for specific users or groups. It can diverge, oscillate, lots of potential problems.
That sounds like a fundamental obstacle. How are people trying to fix this non-IID problem?
There's a lot of research here. It's a very active area. Several main strategies are emerging.
Such as?
One idea is client clustering. Try to group clients that seem to have similar data distributions.
And maybe train slightly different models for different clusters.
Potentially, yeah. Or adjust the aggregation strategy based on clusters. Another approach is using meta-learning.
Meta-learning. Learning to learn.
Kind of. Trying to train a model that can adapt quickly and effectively to the specific data distribution of a new client, even if it's different from others.
Okay.
And then there's a big push towards personalized federated models.
Personalization. So moving away from just one single global model.
Exactly. The idea is maybe the goal shouldn't be one model for everyone. Maybe we want models that are tailored to each user's specific data while still benefiting from the collaboration.
How would that work? Do clients just tweak the global model locally?
That's one way, yeah. Local fine-tuning is a common approach. Train a global model, then each client adapts it a bit using their own data.
Okay.
Other methods involve learning personalized layers on top of a shared base model, or using techniques like model interpolation between a global and a local model, or framing it as a multitask learning problem where each client has its own related tasks,
So lots of different ways to try and give users a model that actually works well for them.
while still getting the benefit of that huge, diverse, federated data set. It's a key research direction.
Makes sense. Okay, another challenge we touched on. System heterogeneity again. Those stragglers,
Yeah.
clients dropping in and out.
Right. It's not just about differing capabilities, but also inconsistent participation. Devices go offline, network connections drop, users stop using an app.
Which must make training unstable.
It definitely complicates things. It makes it harder to guarantee convergence. We mentioned solutions like adaptive client selection and asynchronous training.
Yes.
There's also ongoing work in designing aggregation algorithms that are inherently more robust to these delays and dropouts, things that don't get thrown off too much if some updates arrive late or not at all.
Trying to make the averaging process more forgiving.
Essentially, yes. Making sure progress continues smoothly, even with unreliable participants. It's crucial for real world, especially cross-device FLO.
And the communication bottleneck challenge. We talked compression, asynchronous methods, anything else on that front?
Another technique sometimes used is periodic aggregation.
Periodic, meaning less frequent.
Yeah. Instead of the server aggregating updates after every single local training round on the clients, it might wait for clients to perform several local updates before they synchronize.
Ah, so clients do more work locally between communications.
Exactly. It reduces the number of communication rounds needed overall.
But the downside is?
The global model gets updated less frequently, so it might take longer to converge in terms of wall clock time. Slower learning progress, potentially.
So again, a trade-off. Communication efficiency versus convergence speed.
Always a balancing act. You have to tune it for the specific application, network conditions, and so on.
Right. Now, let's talk privacy and security again. FL is designed for privacy, keeping data local, but you're saying it's not foolproof.
That's a really critical point.
Mm.
Decentralizing the data is a huge step, but it doesn't magically solve all privacy issues. The updates themselves, the gradients, the model weights, can still leak information.
Leak information.
How? Well, sophisticated inference attacks have been shown to sometimes reconstruct parts of the training data just by analyzing the shared model updates, especially gradients.
Wow, really? They can reverse engineer the data from the changes.
Under certain conditions, yes. It's not easy, but it's a theoretical risk that needs addressing. Then you have security threats, like backdoor attacks.
Backdoor attacks.
This is where malicious clients intentionally send poisoned updates. Updates designed to make the final global model behave badly on specific, targeted inputs, like making a face recognition model misidentify a particular person.
Nasty. So adversaries could be inside the Federation.
Absolutely. Or they could compromise clients. And even without active attacks, just sharing gradients can sometimes reveal properties of a client's data set if you don't protect them properly.
Okay, so definitely not inherently perfectly private or secure. What are the technical defenses, the countermeasures?
There's a whole toolbox being developed and used. Differential privacy, or DP, is a really big one.
We hear a lot about DP. How does it work here?
The basic idea is to add carefully calibrated random noise to the updates before they're shared.
Adding noise. Why?
This noise masks the contribution of any single client's data. It provides a mathematical guarantee that an attacker, looking at the aggregated updates, can only learn a limited amount about whether any specific person's data was included.
So it fuzzes things up just enough to protect individuals.
Exactly. But, as you might guess, there's a trade-off.
The noise must impact accuracy.
It often does. More noise means stronger privacy, but potentially lower model accuracy. Finding the right balance is key, and there's a lot of research on doing this efficiently.
Okay, DP adds noise. What else? You mentioned secure multi-party computation, SMC.
Right. SMC includes cryptographic techniques that let the server compute the average update without ever seeing the individual updates in the clear.
Like that secure aggregation you mentioned earlier.
Exactly. Secure aggregation protocols are a prime example of SMC used in FL. Clients use things like secret sharing to encrypt and split their updates. The server aggregates the encrypted pieces, and only the final sum can be decrypted. No one sees the intermediate individual values.
Very clever cryptography. What about homomorphic encryption? HE.
HE is another powerful cryptographic tool. It allows you to perform computations directly on encrypted data.
So clients encrypt their updates, send them, and the server adds up the encrypted updates.
Precisely. The server works entirely in the encrypted domain. Only the final result gets decrypted. It offers very strong privacy.
What? But. There's always a but, isn't there?
The but with HE currently is performance. It's computationally very expensive. Doing those operations on encrypted data takes a lot more processing power and time.
So maybe not practical for millions of phones yet.
It's challenging, especially for resource-constrained devices and large-scale aggregation. Research is ongoing to make it more efficient, but it's not as widely deployed as DP or basic secure aggregation yet.
Okay, so we have crypto for privacy. What about those malicious clients, the backdoor attacks? How do you defend against poisoned updates?
That's where robust aggregation methods come in. These are algorithms designed to make the averaging process at the server less sensitive to outlier or malicious updates.
How do they work?
There are several types. Methods like CRUM try to identify updates that are suspiciously different from the others and exclude them from the average.
Assuming most clients are honest.
Right, it leverages the redundancy of having many clients. Others, like trimmed mean or median, just chop off the highest and lowest values before averaging, or simply take the median update instead of the mean. These are less influenced by extreme, potentially malicious values.
Making the average more stable.
Exactly. And there are more advanced ones, like fool's gold, that try to detect clients colluding over time. It's an arms race, really, between attackers and defenders.
It sounds like it. You also mentioned gradient obfuscation or perturbation. Is that different from DP?
It's related, but distinct. These are techniques aimed specifically at preventing that data reconstruction for gradients we talked about. They might involve things like randomly dropping some gradient values, reducing their precision even further, or adding structured noise or masks.
Just making the gradients harder to reverse engineer.
Yeah, adding noise or distortion specifically to thwart known leakage attacks, sometimes in ways that are less formally guaranteed than DP, but perhaps more targeted or efficient for that specific threat.
Okay. And trusted execution environments. Ts, hardware security.
Ts offer another layer. These are secure hardware zones within a processor. You could potentially run the local training inside a T on the client.
To protect it from other software on the phone.
Exactly. Or the server could perform the aggregation inside a T to protect the intermediate values, even if the server's main operating system were compromised.
Sounds powerful. Are they widely used in FL?
The main challenge is availability and heterogeneity. Not all devices have capable TEs, and managing them across a diverse federation is complex. It's a promising direction, but practical deployment at scale still has hurdles.
Gotcha. And lastly, blockchain again. How does it help with security here?
Blockchain's main contributions here are often transparency and auditability. You can use it as that immutable ledger to record updates, track who participated, maybe even log the aggregation results.
Making things more verifiable.
Potentially, yes. And it can facilitate decentralized coordination or be used to implement incentive schemes rewarding clients for good behavior recorded on the chain.
But the downsides we mentioned before still apply. Latency, energy.
Yes, integrating blockchain adds its own overhead. You need to weigh the transparency and decentralization benefits against the performance costs.
It's clear there's no single silver bullet for privacy and security. You need a layered approach.
Absolutely. Combining techniques, maybe DP plus secure aggregation plus robust averaging, is often the most effective strategy.
Okay, we've covered a ton of challenges. Let's switch gears. Where's all this tech actually being used? What are some real-world applications?
FL is really starting to make inroads in quite a few fields, especially where data is sensitive and decentralized.
Hmm.
Healthcare is a huge one.
How so?
Imagine hospitals wanting to train better diagnostic models, say for analyzing medical images or patient records. They have lots of data, but they absolutely cannot share raw patient information due to privacy rules like APA.
Right, so FL lets them collaborate.
Exactly. They can collaboratively train a shared model using FL. Each hospital trains on its own data locally, only shares the anonymized updates. They get a better model without compromising patient privacy or violating regulations.
That could be genuinely transformative for medical research and diagnosis.
It has huge potential. Disease prediction, treatment effectiveness analysis, lots of possibilities.
What about finance? Another area with very sensitive data.
Definitely. Banks, credit card companies, they're exploring FL for things like fraud detection.
Training on transaction data from multiple banks without sharing it.
Precisely. Or for credit risk assessment, anti-money laundering. By learning from broader patterns across institutions, they can build much more robust models to catch sophisticated fraud or assess risk, again, without exposing sensitive customer financial data.
Makes perfect sense. And didn't you say smartphones were an early adopter?
Yes, absolutely. Edge devices, especially smartphones, are a prime example. Google's Gboard keyboard is probably the most famous early success story.
For next word prediction.
Yeah, and emoji suggestions, too. It learns from how millions of people type on their own devices, aggregates the learning centrally using FL, and improves the keyboard for everyone, without Google ever seeing what you actually typed.
So my phone gets smarter about how I communicate, but keeps my conversations private.
That's the core value proposition for the user. Similar things are used for on-device speech recognition, personalized recommendations in apps, maybe even detecting spam calls, all done locally or with FL.
That's a very tangible benefit. What about bigger scale things? Smart cities, industrial IoT.
Also very promising areas. Think about a city with sensors everywhere, traffic sensors, energy meters in buildings, pollution monitors.
Lots of distributed data sources.
Right. FL could be used to train models for optimizing traffic flow in real time, predicting energy demand to manage the grid better, or identifying pollution hotspots, all using data from these sensors without necessarily having to stream all that raw data back centrally.
Managing complex systems more intelligently and maybe more privately.
Exactly. Or in industrial settings, predicting machine failures based on sensor data from many factories without sharing potentially proprietary operational data. Smart Transportation 2 vehicles could use FL to learn better driving strategies or predict hazards collaboratively.
Collision avoidance, route optimization. Yeah, I can see that. What about language? NLP.
NLP is another great fit, especially for tasks involving user text, personalized language models like we discussed for keyboards, also things like sentiment analysis, understanding opinions in text, maybe for local content moderation, or even building better multilingual models by learning from text in different languages on devices around the world without centralizing all that text.
Training across language barriers without moving the data.
Yeah.
Interesting. And it's not just passive learning, right? You mentioned robotics. Reinforcement learning.
Yeah, Federated Reinforcement Learning, or FRL. This is really exciting. Imagine you have multiple robots, maybe in different factories or homes, learning a task.
Like how to navigate or pick up objects.
Exactly. With FRL, they can each learn from their own experiences in their local environment, but share the insights, the policy updates, or value functions with the other robots via FL.
So they all get smarter faster by pooling their learning, even if they're in different places.
Precisely. It's great for scenarios where training in one shared place is impossible, dangerous, or just too expensive. Think self-driving cars learning from diverse road conditions globally.
It really is striking how versatile this core idea is. Okay, let's circle back one more time to the privacy and security details. We touched on DP, SMC, HE. Let's make sure we've got the technical essence. Differential privacy adding noise.
Right. Applied usually at the client side. Before sending the update, add carefully calibrated noise. The amount of noise is tied to a privacy budget, epsilon. Smaller epsilon, more noise, more privacy, but potentially less accuracy.
It's like deliberately blurring the individual signal just enough.
That's a good way to put it. Enough blur to protect individuals, but hopefully not so much that the overall picture becomes useless. Optimizing that trade-off is key.
Okay. And secure multi-party computation, SMC. Secure aggregation.
This is about computing the sum without seeing the parts, using crypto tricks like secret sharing. I encrypt my update, split it, send pieces around, the server gets encrypted pieces, adds them up using cryptographic properties, and only the final sum is revealed.
The server learns the average gradient, but not my gradient.
Correct. Very powerful for preventing the server itself from snooping on individual contributions.
And homomorphic encryption, HE compute on encrypted data.
Yep. Clients encrypt updates, server adds the encrypted updates, decrypts only the final sum. Very strong privacy, but computationally heavy.
The performance hit is the main issue currently.
It's the biggest practical barrier to widespread use right now, especially on edge devices. But research is improving efficiency all the time.
Got it. And robust aggregation. Dealing with the bad guys. Crumb, trimmed mean.
Right. These are defenses against poisoning attacks. Crumb spots and rejects outliers. Trimmed mean and median ignore the extreme values when averaging. Fool's gold looks for colluders. Different strategies to make the aggregation resistant to manipulation.
Trying to ensure the final model isn't sabotaged.
Exactly. Making the Federation resilient to adversarial participants.
And gradient obfuscation perturbation, making gradients harder to reverse.
Yeah, things like gradient sparsification, quantization beyond just compression, adding noise in specific ways, all aimed at breaking techniques that try to reconstruct data from the gradients.
More layers of defense.
Definitely. And T's, the trusted hardware.
Secure enclaves on the chip. Could protect local training on the client or aggregation on the server. But availability and management are challenges.
Correct. Great potential, but practical deployment across diverse hardware is still tricky.
Finally, blockchain. Tamper-proof ledger for auditability, coordination, maybe incentives.
Yes, adds transparency and trust through decentralization, but brings its own latency and energy costs. Another trade-off.
It really is a multifaceted approach needed for robust privacy and security.
No doubt about it. Combining multiple techniques is usually the way to go.
Okay, well, this has been a really comprehensive deep dive. We've covered a huge amount of technical ground. Let's try to synthesize the key takeaways.
Sure. I mean, fundamentally, federated learning is a major shift, wouldn't you say? It's about enabling collaborative intelligence, collaborative ML, without centralizing sensitive data.
Right, directly tackling those big privacy concerns and regulatory hurdles.
And unlocking potential in so many areas. Healthcare, finance, smarter devices, smart cities. The list goes on. It allows learning from data that simply couldn't be brought together before.
But as we spent a lot of time discussing, it's definitely not plug and play. There are significant technical hurdles.
Absolutely. That statistical heterogeneity, the non-IID data, is a massive one. System heterogeneity, devices dropping in and out.
Communication bottlenecks, always a challenge in distributed systems.
The ongoing need for robust privacy and security techniques, DP, SMC, robust aggregation, protecting against various attacks.
And then ensuring fairness, enabling that personalization we talked about, and just making it all scale up to potentially millions of devices.
Right. These are all very active areas of research. People are constantly innovating new algorithms, better privacy techniques, more efficient system designs. Progress is definitely being made.
So looking ahead, what are the really exciting frontiers? Where is FL research heading?
Oh, lots of places. Personalized FL is definitely a huge focus, getting beyond one-size-fits-all models.
Tailoring models better.
Exactly. Also, bridging the gap between different FL types like cross-silo FL within a few organizations versus cross-device FL across millions of phones. How can they work together?
Interesting. Integration.
Yeah. And trustworthy FL is a big theme. How do we verify the aggregation was done correctly? How do we design better incentive mechanisms so clients want to participate honestly and reliably?
Building trust into the system itself.
Right. And then there are more futuristic things, like federated quantum learning, exploring the intersection with quantum computing.
Wow, okay. That's out there.
It's early days, but Intriguing. More practically, there's a big need for better benchmarking and standardization so we can actually compare different FL approaches fairly.
Making the research more rigorous.
And finally, green FL. Thinking about the energy efficiency. Training these huge models, even decentrally, consumes power. How can we make FL more sustainable?
That's a really important point, too. So it's a field that's still evolving rapidly.
Incredibly so.
Yeah.
It really requires collaboration across disciplines, ML, crypto, systems, ethics, domain expertise, all coming together.
Well, this has been incredibly insightful, a real deep dive into the technical heart of federated learning.
It's a fascinating area with so much potential.
It really is. And it leaves you thinking, as data generation just keeps exploding out there at the edge on all our devices, what other completely new, innovative applications of federated learning might pop up that we haven't even considered yet? Something to ponder. Thanks for sharing all your expertise today.
My pleasure. Always enjoy discussing it.